Howdy folks, there's one more example I would like to take a look at from Chapter 6, and that is an example of recoil. Now, conservation of momentum pops up in all kinds of ways, and recoil is one of those. And any of you that have, fired a gun before are certainly familiar with recoil. Now, in principle, it kind of goes like this. The initial momentum has to equal the final momentum. And that's true for the entire system. So when you have multiple objects, when you combine all of their initial momentum, it needs to equal all of their combined final momentums. Now usually in recoil, things are not moving at first. You've got two objects together, and they're not moving. Like you standing there, pointing a shotgun. You then fire the shotgun, and something goes that direction. Say bullets. The bullets go this direction. Well, now there's momentum in that direction. Well, initially there was no momentum, so if there's momentum in this direction, there better be some balancing momentum in the other direction. That would be you. Or it could have been me. The first time I fired a shotgun up at my grandparents' farm in North Dakota, I about landed on my butt. Instead, I did a nice dance on one leg and managed to stick the landing, saving at least some of my pride. But nonetheless, whenever there's no initial momentum, if something flies off in one direction, something else is going to have to fly off in the other direction. And those things won't always have equal and opposite velocities because they might have different masses. You might have a small object, not so massive, with a large velocity, and then a large object with lots of mass with a small velocity. Now, I usually try to recreate this in the hallways using, a skateboard and a medicine ball. And so that's sort of the idea of this problem. So, I sit on a scooter and I throw a 6.8 kilogram ball with a velocity of -5 meters per second. How fast will I recoil if my mass is 80 kilograms? Which is a little larger than I probably am. Gained a few kilograms since the last problem I did, since we were looking at my weight on an elevator, or on a scale in an elevator, but it's approximately right. I rounded up to the nearest 10 kilograms. It's probably my mass after Thanksgiving and Christmas. Anyway, so let's write down our known information. We were given the mass of the ball, we'll call that M1. We were then given the velocity I throw it with. Now I'm going to call this V1 final. Why am I calling it V1 final? Because that's how it ends. The end of the problem is that ball flying away from me. The beginning is just me sitting on a scooter holding this ball. We begin with no velocity. And that's true for both the ball and for me. My mass is 80 kilograms. We don't know what my final velocity is. That's what we're finding. How fast will I recoil? But we do know that both the ball and me, we're not moving initially. The ball and I were not moving initially. We had velocities of 0. So we're going to solve this with momentum. We've been given masses and velocities. Pairs of masses and velocities certainly should lead you to approach a problem with momentum. If we do some accounting, we know we're going to have two sets of momenta. We're going to have the initial momentum, the mass of the ball times its velocity, plus my mass times my initial velocity. And at the end, there will be two momentums as well, the ball and its velocity and me and my velocity. Well, we just said that the initial momentum is going to be 0 because neither the ball nor myself are moving. We're both just sitting on the scooter. That means m1 times 0 plus m2 times 0 is 0. The initial momentum is 0, and that better equal our final momentum. Well, we want to solve for v2 final, so let's subtract off the other term. Let's subtract m1 v1 final from both sides. If we subtract off m1 v1 final from both sides, we're left with something that looks like negative m1 v1 final equals m2 v2 final. Essentially, it says that object 1's momentum is equal but opposite to object 2's momentum. But that's not really where we stop solving. We want to solve for that final velocity, for me. So we divide by m2 to get my mass away from that velocity. Dividing by m2 on both sides gives us that v2 final equals negative m1 v1 final over m2. And we can plug in some numbers. 6.8 kilograms for m1. Its final velocity is negative 5 meters per second. My mass is 80 kilograms. We multiply negative 6.8 times negative 5. We're going to get a positive number. We divide by 80. And the final number is 0.425. Looking at the units, we have kilograms on top and kilograms on bottom. Those will cancel, and we're left with meters per second. My final velocity would be 0.425 meters per second. And if you recall, the ball flew away with a velocity of negative 5 meters per second. Now, even though their velocities are different, the ball and I have different velocities, our momentums are still equal and opposite. That is, the ball moves faster, it has a larger velocity, because it has a smaller mass. I have a smaller velocity, but a larger mass. And the way these things combine turns out to be equal and opposite. So by launching the ball forwards, I then slowly roll backwards. And we should always expect this type of relationship. If you have two unequal masses and they recoil from each other, the less massive object will move with a larger velocity. The more massive object will move with a smaller velocity. That is the sort of result you should expect. And that's a great example, another simple example of how to apply the principle of conservation of momentum. We'll work some other problems in class, but these give you guys at least a good start, and you can go and check out some of the homework problems at this point. Take care, guys. I will see you next time when we start Chapter 7, Torque.